Okay, I'm going to go over the three problems. Two of them came from the stoichiometry introduction that you did a week and a half ago. I just want to go over a couple things, make sure I say them so that you're aware of them, and show you a couple things that are done. All right, so we're going to start off with question number 1 from that document. It says 3.9 milliliters of oxygen gas at 2.40 atmospheres and 45 degrees Celsius are produced from the decomposition of hydrogen peroxide. How many grams of hydrogen peroxide are decomposed? Okay, so as with all stoichiometry problems, we have to start off with a balanced chemical equation. So decomposition reaction of hydrogen peroxide is going to give you water and oxygen gas. Balanced, you're going to have this. Now this is technically a liquid. This is going to be a liquid. This is going to be a gas. Now we're given information about that oxygen. We're told that we have 3.9 milliliters. We are told that it has a pressure at 2.40 atmospheres. And we are told that it's at a temperature of 45 degrees Celsius. We are looking for how many grams of hydrogen peroxide. Now, the key to this is understanding that when you're doing stoichiometry that involve gases, we have to be given all of these variables because we need to know how many moles. And we don't generally go out and measure moles of a gas. We go out and measure what's the pressure, what's the volume, what's the temperature, because those three things will give us the number of moles. As with all stoichiometry problems, every single one of them, you will do a mole-to-mole conversion in there someplace. That means the very first thing that you need to do is get 2 moles if you do not have moles. We do not have moles of this oxygen, but we can use the ideal gas law to get that moles of oxygen. So we plug in our values, our 2.40 atmospheres, our volume of 3.9 milliliters, but that has to be in liters when you are using the ideal gas law. 1, 2, 3, 9 liters equals in, that's our key, that's going to give us moles. R is going to be 0.08206. Why? Because we are using the unit of atmospheres. And then our temperature is given as 45 degrees Celsius. That corresponds to a temperature of 318 Kelvin. And remember, all problems dealing with gases, if you have a temperature, they must be done in Kelvin. Have to be. Cannot do it any other way. When you solve this out, you are going to get in, so I'm going to rewrite it down here, equal to 3.59 times 10 to the negative 4th moles. And that's of oxygen. Why is it of oxygen? Because these values that we used here for the oxygen are for oxygen. When we calculate this out, this is for oxygen gas. So now we are going to go through, and now that we have the unit of moles, we can do our stoichiometry the way we learned it for a semester. We're going to do our mole-to-mole conversion. 1 mole of oxygen, 2 moles of hydrogen peroxide. And since we're going to grams, 1 mole of hydrogen peroxide is going to give us 34.02 grams of hydrogen peroxide, and you get an answer of 0.0244. Again, the only thing that's different is that we started off with a gas. That means we had to do the ideal gas law first. Then we did our mole-to-mole conversion. Normal, went to grams, ended with our mass. Okay, this is question number 3 from that document. It says when 18.4 grams of iron reacts with water, it's going to form hydrogen and iron oxide. How many milliliters of hydrogen will be produced at STP? Okay, so this time around is reverse what we did before. We're going to start off with normal stoichiometry, and then we're going to end with a gas. So we're going to start off with our 18.4 grams of iron, set up our conversion because we're trying to get to our hydrogen, and 55. Oh, I forgot to balance the equation. 3, 4, 1. Okay, so trying to get to the hydrogen, so 3 moles of iron from the balanced equation are going to equal 4 moles of our hydrogen gas. And we're going to stop here because we want to know how many milliliters of hydrogen gas. Now, it said at STP. Now, this is a good question to cover because STP isn't some mysterious thing. STP means standard temperature and pressure. That means that our temperature is going to equal 0 degrees Celsius, or it's going to equal 273 Kelvin. That's the temperature we're going to have to use because it has to be in Kelvin. Pressure is going to equal 1 atmosphere. Now, you could use 760 millimeters of mercury. I just prefer atmospheres. It's my personal preference. So when you solve out this part of the equation, you're going to get 0.439 moles of hydrogen. We want to know the volume. Because it's a gas, we now know the moles, we know the temperature, we know the pressure. We're going to plug into the ideal gas law. Our pressure is 1.00 atmospheres. Our volume is what we are looking for. Our moles is this value here, 0.439. 0.08206. And our temperature is going to be 273. When you calculate this out, you are going to get a volume of 9.83 liters. The question asks for it in milliliters, so if I just convert that, that's going to give me 9,830 milliliters. Notice this is the reverse of what we did in the first question. We started with a mass, we ended with a gas, and wanted to know the volume of it. Our stoichiometry at the front looks the same. What's different is that we are replacing our final conversion with an equation. Same thing as we did in the first one. We replaced the first step in what we would normally think of stoichiometry with PV equals an RT. We're going to do one more. Okay, in this problem, we have something a little bit different. Basically, we're going to be doing the same thing we did in 1 and 3. We're going to be using the ideal gas law at the beginning and the end. So, again, we have 2 gases in this question. We've got oxygen gas and we've got dinitrogen tetroxide gas. We're given the volume, temperature, and pressure for oxygen. We're asked how many liters of our dinitrogen tetroxide at STP. Remember, this means that we have a temperature of 273 Kelvin and that our pressure is equal to 1 atmosphere. Now, to solve this problem, we start off with the one that we have the most information about. We can find moles of oxygen using this information. So we're going to plug into the ideal gas law. We're going to say pressure is 1.38 atmospheres. Our volume is 16.5 liters. We're looking for the moles. We're going to have 0.08206 And we're going to have our 25 is 298 Kelvin. This one I just made up on the fly, so I'm going to have to solve this out. Times 16.5 divided by 0.08206 divided by 298. That gives me moles of 0.931 moles of oxygen. Now, I need to get to moles of dinitrogen tetroxide. Okay, so every stoichiometry problem has a mole to mole. I have moles of oxygen. I can get moles of dinitrogen tetroxide by using our ratios: 2 moles of O2 to 1 mole of N2O4. And let's stop, because now we want to find what's the volume of this gas. We need 3 of the 4 variables. We've got moles now, so I'm going to divide that by 2. That gives me 0.466 moles of N2O4. Now we can plug back into the ideal gas law using this information and find out what's the volume of our dinitrogen tetroxide. So I'm going to plug in our pressure is 1.00. Our volume is what we were looking for. Our moles is 0.466, 0.08206, and 273 Kelvin. Let's solve it out. And we get a volume equal to 10.4 liters. So in summary, our ideal gas law, RPV equals nRT, is a replacement for a step in our stoichiometry problems, because we don't deal with gases in grams. We deal with gases in pressures, volumes, and temperatures.